Okay, but now let me start explaining what is happening and what I'm trying to get at. Look at this image. What I think you are seeing is 4 bumps, 1, 2, 3, and 4, and 5 holes, 5 shallow holes. Now, needless to say, this is a two-dimensional image. There's no bumps and no holes. But despite that, and undeniably, you are seeing them. And there's nothing you can do about it. That's just the way they appear. Now, look at this other image. Now what you're seeing, I think, is 5 bumps, 1, 2, 3, 4, 5, and 4 holes. In fact, you might notice that this image is nothing but the first image rotated by 180 degrees. So what you saw as bumps here on the left, on the right, they look like holes. Right here, let me show you. Now we're back to having 4 bumps and 5 holes. So what's happening here? Well, see, this image is actually highly ambiguous. What you're looking at can be interpreted and could be interpreted in many ways. And again, your brain is interpreting a two-dimensional picture according to the rules of the world, which means according to the rules of 3 dimensions. Now think of what happens in 3 dimensions. Over time, our minds have developed the guiding principle that light usually comes from above. And that is fairly accurate, right? Particularly on the evolutionary timescale of our species, light typically has come from the sun. So light typically comes from above. Now, if you can assume, as our mind does, that light comes from above, if something is shiny on the top and dark on the bottom, it is likely to be convex. It is likely to be protruding because the light is shining down, is reflecting up here, and the bump itself is then creating a shadow and casting a shadow on the bottom half. So when you see something, even though it's clearly two-dimensional, you can't help yourself but use this guiding principle that your mind has embedded into it. The top, because of this pattern of light and shadows, your brain can't help it but interpret this pattern as a bump. Now, conversely, if something is dark at the top and shiny at the bottom, it probably means that it's concave, which means it's a hole. Because light comes down, it can't really hit at the top, but it can hit the bottom. And so this pattern here, dark and then bright, is compatible with something being concave. Again, there's no bumps and holes in front of you, but your brain can't help it. Your brain has come into this world with certain assumptions, certain guiding principles, certain biases that allow it and that help it interpret what is a very ambiguous signal from the environment. Now, how do you know that what's happening is actually what I'm saying? Well, there's a simple test. If we were to put this gradient of bright to dark in a way that doesn't fit the assumption that light comes from above, it should break the illusion. So if we were to turn this only by 90 degrees, you can either turn your head or wait for me to do it. If we turn this by 90 degrees and the gradient, instead of going from top to bottom, goes side to side, it shouldn't work anymore. Let's try it. So now, this idea that something convex would be shiny on top and dark on the bottom, and something concave would be dark on the top and shiny at the bottom, doesn't work anymore. Right? You can't resolve this image, you can't interpret this image by using those rules. And indeed, chances are these circles now all look probably all flat. At least they look all flat to me. To you, they might either all look flat or all look like holes or all look like bumps. But certainly none of these is giving you the same illusion, the same effect of depth that those on the left are giving you. So although I'm showing you, as I was saying earlier, these little tricks, these little things, I don't mean that there's something wrong with our minds and our brains. I'm just trying to expose, using these cute little tricks, how our minds work. Okay, let me dig a little deeper and start clarifying what I'm trying to get at. Look at this figure. If I were to take the white bar and remove it, what would you expect the black shape to look like? Right? If I just went there and pinched off the white bar, what do you expect to be left behind? Chances are you thought this. Chances are your gut reaction, not your smart answer, your gut reaction is that if I were to pinch off the white bar from here, what would be left is a black bar. In other words, you spontaneously thought that what's happening on the left is that these are two bars. The white one just happens to be including a piece of the black one, happens to be on top of the black. Perfectly possible. Why not? However, could be this. Nothing prevents it from the black shape actually being two shapes, two rectangles, that just happen to be flanking the white one. Why not? Be this image right here fits just as well this circumstance as the one that you thought of. In fact, could be this. Could be that if I removed the white bar, what I would see is a black bar that has in it a hole in the shape of a triangle with a yellow border. Why not? It fits, right? You could totally imagine this being under there. It fits. You know what? Could be this. It could be that there's the two flanking rectangles and a scribble under it. Why not? Could be that there's a black bar and a picture of a famous singer on top of it. It fits. It could be, right? This would still fit this. In fact, I can think of an infinity of possible things that could fit this. I'm sure you could now sit down and create another 100 possible scenarios of things that could be and that then could be consistent with the scenario if you remove the white bar. However, when I asked you, I dare say that virtually all of you, when I asked you what happens if I remove the white bar, you thought of this. And this is the crux of computational complexity. See, the world is extremely ambiguous. There's a ginormous number of possibilities of what could be. The world we live in is highly underspecified in many ways, meaning the information that we receive from the world is often highly underspecified, very ambiguous at times. And there are, in this simple case, there are infinite possibilities of what could be hiding under the white bar. And yet, despite the fact that there are infinite possibilities, 300 students, all right, let's say 299 students in this class all thought this is what's happening. And you know what? It doesn't matter your ethnicity, doesn't matter your gender, it doesn't matter your background, it doesn't matter how many languages you know, it doesn't matter what's the language that you speak at home with your family. None of this matters. You all thought the same thing. And this is how beautiful the human mind is. The world is extremely complex. The computational possibilities that you would have to go through in order to answer this question, the question of what happens if I take off the white bar, is infinity. There are an infinity of possible answers to that question. And yet, your mind spontaneously and effortlessly picked one. This one. The reason is that this is particularly reasonable and particularly plausible in the environment and world we live in. This is also known as the principle of good continuation. We're going to discuss this a couple lectures from now. It's the idea that when two shapes intersect or overlap, we tend to think that shapes continue in a smooth manner. So it makes sense. The simplest explanation, the one that fits with how objects work in the real world, is that these are two bars, one on top of the other. It's what works in this world. See, our mind through evolution has developed a number of guiding principles, a number of biases, of proclivities that allow it to answer questions that potentially have an infinite number of answers. Our mind has developed a number of strategies, strategies, these preferences, these guiding principles, these biases that allow it to answer questions that potentially have an infinite number of solutions. The computational complexity of finding all the possible answers to this is huge. If you were a computer, a smart computer, and I asked you this question, hey, what's under here? You would have to start spitting out an infinity of possible answers. And then once you find out the infinity of possible shapes that fit this, you have to pick which one is the good one. Our minds don't do that. Through evolution, through interacting with our environment, we figured that most of the times what's happening is two smooth objects, one on top of the other. Sure, it could be this. 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 You know what? Most of the times, it's this. So our minds have developed these strategies, these rule of thumb, these guiding principles, these biases that allow us to quickly solve problems that are computationally impossible for us to solve in a brute force type way. This is the idea of computational complexity. The idea that there are too many possibilities to be considered and no general purpose ways of resolving ambiguity. So human cognition, you can think of it as a specialized form of intelligence, a form of intelligence that is adapted to interacting with the environment we exist in. Again, through evolution, our minds have developed a number of guiding principles, biases, preferences that allow us to cope with an environment that, in terms of its computational complexity, in terms of its ambiguity, exceeds our computational capacities. Our minds don't have the strength and the computational power to go over all the infinity of possibilities that could answer that question of the two bars. So instead of going through all the possibilities, somehow we've developed a way of knowing which is the most likely one. And mind you, when I asked you that question, you didn't effortfully think, let me think about this one. I think it's probably this one, or I think it's most likely to be this and that. That's just what came to mind. Your mind did that for you. You didn't effortfully